we can also write down that because we know there are two different parts of the voltage, we can separate the voltage as two functions. The same as our E field and H field. We know if it is time harmonic, or we say our voltage is sinusoidal steady state. We can understand the equation of Vt. We can just directly use exponential J omega t as this part. So you can write down my voltage, it is a function of Z and T equals my voltage of Z multiplied by exponential J omega t, this part. Okay, the same as our E field and the H field. When we say it is time harmonic, we just take the function of time. We use this equation, this part, this fraction, this part as our function of time, okay? So, which means when we try to say something relevant to our voltage Z, T, voltage of position and the time, we talk about the partial differential of our voltage to our time. We always can use the relationship, the same in our chapter 1, okay? We write down J omega V okay, we can do something like that. Which we have something, and we have something for the voltage and the time here. If you write down the Kirchhoff's voltage law equation, the equation about the Kirchhoff law, the voltage here equals to the voltage drop from here to here, plus the voltage drop from here to here, plus the voltage here. Okay, that is the equation. So the rate one, first one, equals to the voltage drop of a resistor. It is the current, which is I of Zt multiply your resistance. R is the average resistance, so you need to multiply your distance, delta Z. So this is the total resistance multiply your current. This is the voltage drop here to here. Okay? It's the potential difference between these two on this resistor. Also, refer to your maybe the old knowledge you should know. There is a total inductance, means the average inductance multiply your delta Z multiply. If you want to see the voltage difference between the inductance, you use this equation, right? The total inductance multiply your current partial differential respective to the time. Remember, it is time, okay? And then this part, it is J omega according to this one. Of course, this is voltage, but this is inductance. But they have the same reason, because their time is exponential power to j omega t. So if you do the partial differential to the time, always equal to j omega. So j omega L multiplied by I. This is the voltage drop from here to here. Okay, and plus the voltage here. The voltage here is V at Z plus delta Z. Okay, the red one equals to 3 yellow voltage drops. Okay, this is a Cauchy-Hopf voltage law for the first equation. Let's try another one, another extra point. Anyone want to try the current law, Cauchy-Hopf current law? Anyone? Extra. Anyone? I think somebody did the voltage law. How about a current law? Anyone want to try? Raise your hand. Come here and show us what the Cauchy-Hopf current law. So the current
here is in, this is go out, go out, go out.
So the
This,
total current.
This equal this is this equal this plus this plus this.
Yes, correct. Okay, it's not so difficult, right? So the current law, Cauchy-Hopf's current law, the total current here, the input current here will equals to 3 current. Current here, and current here. Okay? The blue one, IZT equals to the voltage at here multiply our conductance, the total conductance means the current here. This is the first one. Plus this equation, the total conductance multiply the voltage here, take the partial differential with respect to the time. You will get another current here, and plus the current outside. Okay, so now we have two equations. One of that from Cauchy-Hopf voltage law, another one is from the current law. Now we write down, just bring it again. Okay, I write down those two equations. I try to multiply 1 over delta z. Sorry, Abby, I write down in the use Chinese here. This means multiply by 1 over delta z. Or I can say I move my delta z from the right hand side to the left side. Okay, I move all the delta z from here to here. So these two equations become these new equations. Okay, and you can see that for this equation, you have very similar thing at the right hand side. Okay, let me circle it. For the second part of these two equations, you have this one, looks similar to this one. What's different? The difference is the position. This is a voltage over position, and the voltage at another position over the actually these are distance between this position, okay? They look similar. I'm trying to take this one to this way. This part subtract minus this part, okay? And these two terms move to the left side. So I write down like this way. And at the beginning, I told you my delta 0 is very, very small. Okay? So you know this before, like if you see this equation, you subtract this term to this term, they have different, the voltage at different position divided by the distance, and the distance is very, very small. This part equals to a partial differential. Okay? This is actually very general definition you should ask the professor in calculus, okay? I think you should maybe know this before. So this term equals to here, equals to, because I moved this to another side, remember, right? So you take the minus sign of Ri minus L, and this is your current divided by T. For this is the first equation and second equation, you have very similar form. These two equations are very, 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 very important. How many very I said? Very, 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 very important. Okay. We will call them telegrapher's equations, or we will call them transmission line equations. High frequency transmission line equation. Okay. This relationship, these two equations are very, 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 very important. For the rest of the series will be derived from these two equations. Okay? This is the beginning, like the Maxwell equations. This is the beginning of our transmission line theory. We will use them a lot of time. Okay? And if you do a very similar thing, you will see, actually you take this one, but because your delta z is very similar to 0, right? It's close to 0, maybe you can disregard the delta z here. You will have two beautiful equations, looks similar. Okay. Remember the name of these two equations? The name is telegrapher's equation. You know what is telegrapher? Is that like a typewriting? Yeah. In Chinese, 电报方程式. Okay. Telegrapher's equation. Looks similar, familiar or not? Are you familiar with two equations? Maybe not yet. Let me try to simplify these two equations and maybe you will understand. Okay. First of all, let's read it at the beginning. This is a partial differential to our voltage with respect to position. See, this is Z, okay? Equals to the average resistance minus average resistance. Average, this is not total, this is average resistance. Multiply my current minus my average inductance, multiply the current partial differentiate to time, this is J omega. Right? See? So if you do something, every time you see this, you can change to J omega because of this relationship. Okay. So actually, something differential to respect to the position equals to R I is average R I minus average L J omega L I. This is J omega L I, and this is I. Okay. So for this part is R. This is J omega L. Did you discover something? We can write down. Let's write down. So let's read these two equations carefully. I have a voltage. Okay, the voltage of it is a function of the position and the time. I take a partial differential to position will equals to minus R, right? Multiply our I is also a function of the Z and the T, and this one minus, I told you that is J omega for the partial differential respect to time part, okay? J omega L multiply I, right? I can also take my exponential part away because this is not relevant to time, right? So I write down like for this one, partial V Z, partial Z multiply exponential J omega T equals to, and I combine, they have I and I here, I combine them together, equals to minus R minus J omega L multiplied by I of Z multiply exponential J omega T. I took exponential J omega T away again. Okay? I can take them away because both of these two signs is the same thing. And what's this? Is that minus Z, right? R plus J omega L, it is Z. It is Z, right? Okay. And we can do similar thing here and then there. Okay. I just try to help you to read through it and we can continue. Okay. So this is the same as I wrote down there for the first equation. And the second equation, you have very similar result. Okay? You guys need more time to digest, to understand, to check if I make mistake or. Okay.
它学的地方是它可以地，就是
Yeah, I think it's the same. Partial is okay.
它学是两个，它如果左边
哦，只有一个就 D 就对了。Okay, okay. Definition. You know what I mean, right? Okay. Partial means there are two maybe you are the professor in the calculus. Okay, yeah, you are right. You are right. If you take that away, maybe you can change that to, because you have only one thing to differentiate. Use that. Okay, this is more accurate. Thanks. Okay, so you can use that. So this one transfer to this one come P. Okay, so we can continue, right? Now we have these two new equations. They look beautiful, right? Similar. That it's easier. They look easier. Okay. When we are in chapter 1, we start from the Maxwell equations. Do you remember that? The first and the second Maxwell equation, it is a curl E equals to minus J omega something H, and the curl H equals to J omega E. Remember the first Maxwell equation and second Maxwell equation, right? Faraday's law and Ampere's law, remember? Looks very familiar. It looks very familiar because I see something about the differential that is a curl, but now it's a differential with respect to z for left part. For the right side, I see something j omega something and multiply to I. For that, I multiply to h. V, I, V, E, H, H, E. Similar, right? Very similar, right? Okay. So what did we do for these two equations? Do you remember? What did we do? They look, yeah, I say it's very similar, except for this one we have this term, but for that one we have that term. Do you know why? If you consider R and the G, it is lossy. This is a lossless case. If you consider lossless, you don't have R and G. They are more similar. Okay? They are more similar. As I say, voltage, current, H field, E field, H field, they have some connection. They have some connection. You can see voltage and current, E field and H field, the types. Okay. So what we did before is we differentiate Z again, and when we differentiate to Z, you can take this part, right? You will have this part. For this part, you keep this part, and you take the differential to from I divided by dz. And then this term equals to this term. So what you need to do is, first, you write these two equations down. Okay? Second, you take another partial differential to z, maybe not partial differential to z again. Okay? If you take differential to z again, here you keep this term, and then this part become this part. Right? And then you can directly move this part inside. And you will have these two equations. Understand? The same as what we did in chapter 1. Remember, when we do the wave equation, we solve the wave equation, you take the curl to your Faraday's equation, right? For this part, you just use another equation, the result, this equation directly put this part inside here. And then we mark it. So the red part is here, right? So what you need to do is just use this result instead of dIdZ. Move that here. So you will have the result is the D, I don't know how to pronounce, the second order.
Double differential. Double differential.
Double
Differential.
differentiate. Okay, thank you. Double differentiate. Can I say the second order of
Yeah.
Okay. Of this part equals to this term multiply this term. Yeah, I move that here, and I also keep the VZ here, right? And because of minus times multiply minus is plus, but I move from right side to left side, so I have a minus side again. Okay, so they are our new equations from the telegrapher's equations. Too fast? If you don't follow, please tell me, okay? I use two telegrapher's equation. I take the V to the Z again, to the left part and the right part. And I use this result instead of this part. So you get these two equations. And now we can define a new parameters. We call this red one gamma square, which is a combination of R, L, G, C. This one looks like a Z, right? And this one looks like a Y. Okay? This is the average Z and average Y of my transmission line. Remember, this is average, okay? Okay? So this is gamma squared. Okay. Keep moving. And what can we do from these two new equations? This pair of equations. We have the relationship of our voltage, take the second order of the differential respect to Z, the second order, the square, okay, of our voltage, minus gamma square multiply our voltage again equals to 0. See? Voltage take the second order of differential to Z minus something multiply your voltage equals 0. Voltage equals 0. Current equals 0. I can solve what does voltage or what does the current looks like. What does they look like, okay? I can solve this equation to understand what is the structure of voltage and I can also solve this equation to understand what is the structure of current. Okay, understand? The same as what we did in chapter 1. In chapter 1, we solve the wave equation, right? And we know what does the E field looks like and what does the H field looks like. Remember? It looks very similar. Now our gamma is a combination of our lumped elements. See? So it is very important to learn chapter 1 because they look totally the same. The voltage and the current and the E field and H field looks the same. The difference is this is a vector, but this is not. Actually, it's easier, right? They are scalar function. They are not a vector function anymore. It is easy to run. This is hard to run. Vectors, spatial vectors, right? And this is only scalar functions. They look the same. The relationship of the current and voltage are the same as E and H. So the formation, the form, the structure of voltage and current is the same as the E and H. Okay, so when you learn in chapter 1, your E field looks like this way, right? Because you solve the wave equation. In chapter 2, your voltage and the current is supposed to be looks very similar like this form. So they are the voltage and the current on our transmission. Understand, everyone? This is why we need chapter 1. Okay? Because they are the same. The structure the same. So your voltage, now you know there will be questions, right? We will have new questions now, right? You know there will be maybe in the final exam, you need to write down what is the voltage and the current. The same as in your midterm, right? But now you are more familiar with these two equations because they are very similar to the E field and the H field. Your voltage will equal to two voltages. One is the voltage wave propagating in positive Z direction. One of the voltage is reflected, we call it is traveling to the negative Z direction. This is the first part and second part. So for this part, this is V plus 2 as a function of Z. Okay? This is a positive, a voltage wave moving in positive Z direction. And this one is a voltage wave moving in a minus Z direction. Okay? Similarly, there will be two current waves moving in different opposite direction. Positive Z direction and a negative Z direction, okay? Okay? The same, similar to your E field and the H field. They have two parts, positive and negative. they have two parts, right? Positive and negative, positive and negative. And now in this case, you have gamma. We defined a gamma 2 pages ago, right? Two pages. It is equals to the square root of r plus j omega L multiplied by the factor of g plus j omega c. R, L, G, C, they are all of them are average lumped values of the transmission line. I have a transmission line. I have different R, average L, average G, average C. Because you have R and a G, so this is a lossy transmission line. If it is a lossless transmission line, you are very happy that maybe in my midterm I will use many of the cases the lossless transmission line. So you will have a R equals to 0 and the G equals to 0. Okay, that's a good thing, right? Okay, so the gamma, sorry, this is gamma. Did I say R here? It's the gamma. Gamma is a propagation constant. Propagation constant. We define that. Okay, 3 pages from here. We call this term gamma squared. So gamma is the square root of this term, okay? Can you guys accept can you guys understand? And I can go on. I can still go on, but I'm afraid that you don't follow. There will be meaningless. But you can follow. I can give you more. You can learn more. Okay? Now it looks okay. Okay. Let's go on. Yeah. Because for my opinion is that it's easier than chapter 1, right? If you understand chapter 1, now it's easier because the same. But in chapter 1 it's vector, now it's scalar, easier. Everything is the same, the result is the same. Except a little bit different, but you need to understand. Okay? So now we can derive one important thing. Okay. Let me use this one to derive. The 10 minutes, you can stop here. Let me do the last derivation. Okay, you need to take this, it's important. Let me write it down, okay? I just write it down, but I will use my way to explain. It will be easy for you to understand, okay? Even what I want to say is already on the PowerPoint, but I want to do that step by step and make you understand. So, the result we obtained so far is my voltage. It is a function of z. We took the time component out. Now we look at, if you want to see a time, you just multiply the exponential j omega, it's okay. So we can make it easier to understand. So my voltage of z will equals to the positive voltage of z plus the negative voltage of z. There are two voltage waves, okay? And for the first part, it is, use the V01, some magnitude. This is some magnitude, like your E field. Remember E0, right? E0 plus. So voltage 0 plus. I don't know. Maybe I will give you a number in the final. This is the number. Multiply my exponential minus gamma z. Okay. Plus V0 minus exponential positive gamma gamma Z. V, the total voltage is the positive voltage plus a negative voltage. I write down something, maybe I don't know the magnitude. It's okay, I will give you a magnitude in the test. And there is a gamma, right? Remember K, right? K is easier. K is just only beta. Gamma equals to alpha plus J beta, remember? And here also equals to the square root of the R plus J omega L and G plus J omega C, right? For the lossless case, R and G is 0. What happened here? If R is 0, G is 0, this is lossless. J multiplied J is minus 1. Okay, let me write down. Will become minus omega square root omega LC will equals to J omega square root of LC. This is beta for K. K equals to omega multiply LC. Something familiar? Okay. Maybe I will ask this later, but this is not what I really want to tell you here. Okay. So the voltage, total voltage, is a positive voltage plus a negative voltage. Similarly, the total current equals to, I can just copy it. This is the R, this is gamma plus I0 minus, and okay, I have voltage and the current, and I also have the relation of this is a telegraphy equation, right? If I take dV of dz equals to minus R plus J omega L multiplied IZ. Okay, this is one of the telegrapher's equation, right? I put the voltage and the current, total voltage and current here. This one equals to, if I want to do this one directly, I take this one respect to differentiate to z. What is the result for this one? So I have minus R for this part, minus gamma multiply V0 exponential minus gamma Z plus gamma V0 minus and plus gamma Z. Right? The same as I write down, right? And for this part, I transfer this part to this term. So I put this part as this part. I minus gamma Z plus I Z 0 minus. You guys follow? What do I want to make the equation? For the equation here, should equals to the equation here. These two equations should be the same, right? Did you follow what when I changed the equations? So this is what I try to derive the blue arrow part. So this equation equals to this equation. Okay? Because we know your voltage separate to positive and negative, and your current separate to positive and negative. So, therefore, we can take only a positive part equal to our positive part, and the negative part equal to our negative part. Okay? Okay, guys? Right? This is the positive part, right? So this part multiply this parameter should equal to this positive part. Let me write down. I separate the positive part and negative part. So the positive part is I use the voltage equals to, okay, so minus gamma V0 plus exponential minus gamma Z equals to minus R plus J omega L multiplied by I0 plus exponential minus gamma Z. Okay, this is the positive part, right? You got it? I can take the exponential away because they are the same. Therefore, I can obtain a result between the ratio of V0 plus over I0 plus equals to R plus J omega L over gamma. Okay? Equals to, you know, gamma equals to the square root of R plus J omega L multiplied G plus J omega C. This term can cancel out and you can have this one. You can have the square root of this one. So you can obtain this term equals to you take the V0 plus over I0 plus equals to the square root of R plus J omega L divided by G plus J omega C. What's this? This is the magnitude ratio of positive voltage to the positive current. We define this, we call them V. We define this one, we call Z0. And the English name of this one is characteristic impedance. We use 50 ohm on our VNA. We use that in many ways. Sometimes many of them use 15 ohm. This is the definition of characteristic impedance. It is positive voltage, the magnitude of positive voltage to the magnitude of the positive current. You can also try your negative part. You will obtain that there will be a minus sign. For the negative part, because the direction of current is different, the direction of voltage is the same, but direction of current is different. So there will be a minus sign. Okay. This is extremely important because this is how we define characteristic impedance. Okay? Okay, this page is very important. Z0. You use that a lot. You use that a lot. This is how we derive it. Okay, let's take a break.